In today's assignment, we are going to look at p-n junctions. This is assignment 5. In assignment 4, we looked at metal semiconductor junctions. In assignment 5, we are going to look at junctions formed between p and n type. So, usually the p and n are of the same material, in which case it is a homo junction. We have also seen hetero junctions, where the junction is formed between two different materials. In this assignment, we will focus fully on the homo junctions. We will do some calculations on the built-in potential when a junction is formed, the depletion widths, and that is the total depletion width, and also the depletion width on the p and the n side. A p-n junction is essentially a diode. It is a rectifier, so that it conducts current in the forward bias and does not conduct in the reverse bias. So, we will also do some calculations of the forward bias current and the reverse saturation current. So, some of this will be similar to what we did in assignment 4, where we looked at a Schottky junction, which is also a rectifier. So, later we can compare the properties of a p-n junction and that of a Schottky junction. So, let me go to problem number 1. We have a silicon p-n junction which has an n region with 10 to the 17 donors per centimeter cube, n region. So, Nd is 10 to the 17 per centimeter cube, and there is a p region with acceptor concentration of 2 times 10 to the 17 per centimeter cube. Na the material here is silicon and it is at room temperature. So, temperature T is 300 Kelvin. The intrinsic carrier concentration, we have seen this so many times in the past, is just 10 to the 10 per centimeter cube. So, in part A, we want to calculate the built-in potential of this junction. So, V naught is the built-in potential. So, it is the potential when the junction is an equilibrium, and this forms because we have electrons from the n side moving into the p side. This is a diffusion current. We have holes from the p side moving to the n side. These essentially meet each other and annihilate, so that you have a depletion region. So, on one side of the depletion region you have a net positive charge, this is the n side. On the other side you have a net negative charge, that is your p side, and there is a junction potential that develops. So, this built-in potential is nothing but kT over E ln of Na Nd over Ni square. So, this is just a direct substitution of the numbers. Na and Nd are given, Ni square is also given. If Ni is not known, you can always calculate Ni from the band gap and the effective density of states or the effective mass of the electrons and holes. So, you can just plug in the numbers and the answer is 0.852 volts. In part 2, we want to calculate the total depletion width. So, let me call that W. that is the total depletion width. So, the depletion width again forms because you have electrons and holes moving across the junction and are recombining. So, we have seen this concept of a depletion width earlier when we looked at a Schottky diode or a Schottky junction. In that case, the depletion width is almost entirely on the semiconductor side. So, here the depletion width will be in both the P and the N side. So, the total depletion width is again just given by a direct formula substitution. So, 2 epsilon naught epsilon r N A plus N D times V naught, where V naught is your built in potential, by E N A and N D, and the whole to the 1/2. So, epsilon naught is the permittivity of free space, epsilon r is the permittivity of silicon, the relative permittivity, and epsilon r is 11.9. So, that is a known value for silicon. So, once again everything here is known, we just calculated the built in potential V naught. So, we can do the substitution, and this works out to be 1.3 times 10 to the minus 7 meters, or if you want to write in nanometers, 130 nanometers. In part C, we want to calculate the depletion width on the P and the N side. So, the ratio of the depletion widths WP over WN is inversely proportional to the concentration of your dopants. So, this is equal to ND over NA. Another way of writing this, of course, is that WPNA is WDND, and this comes from the charge neutrality, so that the total positive charge due to your positively charged donors on the N side must be equal to the total negative charge due to the negatively charged acceptor ions on the P side, and those two essentially balance. We also know that total with W is just WP plus WN, and total with W has been calculated to be 130 nanometers. So, we have all the numbers. It is again a case of doing the substitution and the math. So, I will just write down the final values. So, WP is 43 nanometers and WN is 87 nanometers. So, the total width comes out to be 130 nanometers. The acceptor concentration on the P side is higher, so 2 times 10 to the 17. So, the depletion width on the P side is smaller. So, let us now go to problem 2. Problem 2, we have a PN junction diode with a concentration of 10 to the 16 acceptor atoms on the P side and 10 to the 17 donor atoms on the N side. So, once again you have P side and the N side. So, Na is 10 to the 16 and Nd is 10 to the 17 per centimeter cube. So, we need to know the built in potential if the material of the semiconductor is different. So, in this particular case we want the built in potential for the semiconductor materials germanium, silicon and gallium arsenide. So, if you go back to the formula for the built in potential, kT over E ln of Na Nd over Ni square. So, if you change the material and if you keep the dopant concentrations the same and the temperature is also same, it is typically room temperature, the only thing we are changing is Ni. We have seen earlier that Ni depends upon the band gap, square root of Nc Nv exponential minus Eg over 2 kT. So, as the value of the band gap increases, Ni essentially goes down because it has an exponential with a negative term. If the value of Ni goes down, then the built in potential will essentially increase. So, in this case we have 3 materials. So, I will write down the table that is given in the problem. So, we have germanium, silicon, gallium arsenide. The band gap values are given in Eg and these are mainly used just for comparison. We do not need the band gap values as far as this problem is concerned. Germanium is 0.7, silicon is 1.1, gallium arsenide is 1.4. What we do need is the values of Ni, and Ni is again given per centimeter cube. So, germanium is 2.4 times 10 to the 13, silicon is 1 times 10 to the 10, and gallium arsenide is 2.1 times 10 to the 6. So, Ni essentially decreases as the value of the band gap increases. So, we now need to calculate the built in potential for these 3 materials. We can make use of this formula, just substitute Na and Nd and then the values of Ni for the different materials. So, we can go through and work out the math. I will just write down the final answer. So, V naught, which is your built in potential, is nothing but 0.372, the units is volts. For germanium it is higher for silicon 0.775 and it is even higher for gallium arsenide 1.213. So, as the value of Ni goes down because you have a higher band gap, the built in potential at the junction essentially increases. So, this information is especially useful when you are trying to build devices with materials apart from silicon, because once you know the built in potential, you would also know what kind of current that needs to be applied through the circuit for a particular kind of application. Let us now go to problem 3. In problem 3, we have a silicon abrupt junction which is in thermal equilibrium at room temperature. So, temperature T is 300 Kelvin. It is doped in such a way such that Ec minus Ef is 0.21 electron volts in the N region. So, you have an N region and you have a P region. So, in this question the doping concentrations are not given, but the position of the Fermi level is. So, here Ec minus Ef is 0.21 electron volts and Ef minus Ev is 0.18 electron volts. The material is silicon, So, some of the parameters of silicon Ni, which is 10 to the 10 per centimeter cube, the band gap of silicon Eg is 1.10 electron volts. The position of the intrinsic Fermi level EFI, it is not exactly at the center, but it is very close to the center. So, we can take this as 0.55 electron volts. So, these are some of the parameters of intrinsic silicon that we can use. So, the first part of the question says draw the energy band diagram for the p-n junction. So, before we do that, we have to first draw the energy band diagram for the two regions separately, and then we can put them together to draw the energy band diagram for the junction. So, on the n side, this is my conduction band, this is my valence band. This gap is nothing but Eg, which is 1.1. EFI is at the center of the gap, so that is 0.55, and Eg is 1.1. So, this question says Ec minus Ef is 0.21. So, the Fermi level on the n side EFn is 0.21 electron volts. So, this height, which is nothing but 0.55 minus 0.21 is 0.34. So, all the energies are in electron volts. I am just not writing the units, but everything is in eV. We can now do the same for the p region. So, the material is the same, so the band gap is the same. Let me just draw this slightly better. So, it is the same silicon. So, Ec and Ev are located in the same place. EFI will also be located in the center. EFI. In this particular problem, Ef minus Ev is given to be 0.18 electron volts. So, EFP so this is 0.18. So, EFI to Ev is 0.55, so that this height is nothing but 0.37. So, this is 0.55, this is 0.18, this is 0.37. So, we have the energy band diagrams of the n and the p region separately. We can put them together and draw the energy band diagram of the p-n junction. But before we do that, I would like to calculate the concentration of electrons and holes on the n and the p side. So, that we can do by basically using the formula EFn minus EFI is kT ln n over Ni, and EFP minus EFI is equal to minus kT ln of P over Ni. So, the position of the Fermi level is related to the concentration of the majority carriers. On the n side it is your donors, on the p side it is the acceptors. So, here this term is known and this is the unknown, same way here this is known and this is the unknown. So, EFn minus EFI is 0.34 and EFP minus EFI is minus 0.37. So, we can substitute in the values, so that we get N equal to ND, which is equal to 5.1 times 10 to the 15 centimeter cube. P is nothing but Na, is slightly higher, 1.62 times 10 to the 16 per centimeter cube. So, even without doing the numbers, we could have predicted that Na will be higher than Nd, simply because the Fermi level on the p side is located is closer to the valence band, it is only 0.18 compared to the Fermi level on the n side, which is 0.21 electron volts below the conduction band. So, we have drawn the energy band diagrams separately. We also have the concentration of the electrons and holes. So, let me draw the energy band diagram when the junction is formed. To do that, we know that the Fermi levels must essentially line up at equilibrium So, this is EFN, this is EFP. Far away from the junction, you still have an n type semiconductor and you still have a p type semiconductor. Let me just arbitrarily mark an interface between these two, and we can show the bands bending. So that these two join. So, this is EV, this is EC, this is EC, this is EV. So, you have the Fermi levels lining up and there is a built in potential, this is a straight line, and there is a built in potential V naught formed at the junction. So, part B, we need to determine the concentration of the impurities. So, we actually just did that. So, this is essentially part B. Just by looking at the shift in the Fermi levels, we can calculate the concentration of the impurities. Part C, we want to calculate the built in potential. So, V naught is nothing but kT over E ln of Na Nd over Ni square. We can do all the substitution and the numbers. So, this works out to be 0.71 volts. We can also calculate the built in potential by looking at the energy band diagram. So, in this particular case, the distance between EFN and EFP. So, this distance is essentially 0.34 plus 0.37. So, this distance delta is 0.34 plus 0.37, which is 0.71 electron volts. So, when the junction is formed, we know that the Fermi levels have to line up. So, we can think of as either the n side shifting completely by 0.71 or the p side shifting up by the same 0.71, so that they line up. So, the built in potential or the built in voltage is nothing but the difference between the Fermi level positions. So, this is 0.71 electron volts. If you divide by E, it is 0.71 volts. So, instead of using the formula, you can also calculate the built in potential by just looking at the energy band diagram. So, let us now go to problem 4. So, in problems 1 to 3 we looked at the p-n junction in equilibrium, so that there was no external potential that was applied and no current that was flowing through the junction. In problem 4, which is slightly a long problem, we are going to look at a p-n junction that is essentially biased, and we are going to calculate some values for the current in the forward and the reverse bias. So, problem 4, you have an abrupt p n plus junction So, when we say a p n plus or a n p plus n, the plus essentially denotes that this is heavily doped. So, when one of the carriers or when one of the sides of a p n junction is heavily doped, then the depletion region lies almost entirely on the other side. So, one way to see that is to go back to this equation. So, N A W P is equal to N D W N. So, when N D is much greater than N A, this implies W N is much smaller than W P. So, that the depletion width is almost entirely on the P side. I will also just write the reverse. When N A is much greater than N D, then you have W P much smaller than W N, and the depletion is almost entirely on the N side. So, we have an abrupt p n junction. The cross sectional area A is 1 millimeter square. We will use the cross sectional area to calculate the current. The acceptor concentration of 5 times 10 to the 18 boron atoms on the P side. So, Na is 5 times 10 to the 18 per centimeter cube, and there is a donor so this is boron, there is a donor concentration Nd is 10 to the 16 per centimeter cube, and this is arsenic. So, in this problem Na is much higher than Nd. So, this should actually read P plus N, not P n plus, it is my mistake, because Na is much greater than Nd. So, we have 5 times 10 to the 18 boron and 10 to the 16 arsenic atoms on the N side. The whole lifetime values are also given. So, the lifetime of the hole tau h in the N region. So, these are your minority carriers. This is equal to 417 nanoseconds. Similarly, the lifetime of the electrons in the P region is only 5 nanoseconds, and this difference is because of the difference in concentration of the dopants. The thermal generation lifetime is also given. So, tau g is 1 microsecond. Some other values are also given for this problem. So, mu e, which is the mobility of the electrons, so 120 centimeter square per volt per second. Mu h is 440 centimeter square per volts per second. Eg is 1.1 eV. The length of the P and the N regions are also given. So, you have a P region width is 5 micrometers and the N region width is 100 micrometers. So, these are a whole set of data that is given about the silicon p-n junction. So, the first thing we need to calculate is the minority diffusion length and to determine what type of diode this is. So, we want to calculate the minority diffusion lengths. So, in the case of a p-n junction under equilibrium, you have a dynamic equilibrium, so that electrons and holes are moving across the junction and constantly get annihilated. When we apply a forward bias, the p side is connected to the positive, the n side is connected to the negative. The Fermi levels no longer line up, but essentially get shifted, and when this happens, the barrier comes down. So, V naught is the built in potential or the barrier during equilibrium. When you apply an external potential, the barrier is V naught minus V external. When the barrier goes down, we basically have minority carriers moving across the junction. So, we have electrons from the n side moving to the p side where they are minority carriers. We also have holes from the p side moving to the n side, and there they are the minority carriers. So, it is this minority carrier diffusion that essentially causes current to flow in a p-n junction. So, the first thing we want to calculate is the diffusion lengths. To know the diffusion lengths, we need to know the diffusion coefficients. So, dE, which is the diffusion coefficient of electrons, is nothing but kT mu e over E. So, it depends upon the mobility, and dH is kT mu h over h. So, the values of mu e are given, mu h is given, everything else is a constant. So, we can plug it in. So, that dE is 3.10 centimeter square per second. dH is 11.39 centimeter square per second. So, dH is higher than dE because mu h is higher than mu e, and this is because the holes are diffusing on the n side and the concentration on the n side is 2 orders of magnitude less than the p side. So, because you have less concentration of your dopants, the diffusion coefficients are higher. From the diffusion coefficients, we can calculate the length. So, L is nothing but square root of d times tau. So, Le is dE tau e, Lh is dH and tau h. So, once again dE and dH we have calculated, tau e and tau h are given. So, we can substitute the numbers. So, Le works out to be 1.2 micrometers. I am not doing the math. So, all your units are in centimeters. So, your answer will also be in centimeters, you can just convert that into micrometers. So, Le is 1.2 and Lh is larger, it is 21.8 micrometers. So, if you looked at the length of the diodes on the P and the N side, on the N side the diode length is 100, on the P side the diode length is 5 micrometers. So, LE is smaller than the 5 micrometers, which is the length on the P side. LH is smaller than 100 micrometers, which is the length on the N side. So, that this is essentially a long diode. So, a long diode is one in which the diffusion lengths are smaller than the physical lengths of the P and the N region. So, this is part A. Let us go to part B. So, in part B we want to calculate the built-in potential across the junction. So, this is the potential when the junction is in equilibrium. So, this is fairly straightforward. So, just kT over E ln of Na Nd over Ni square. So, we have all the numbers, we just need to substitute that. This works out to be 0.877 volts. So, this particular problem does not ask you to calculate the depletion widths, but you can go ahead and do the calculation and you will find that the depletion width is almost entirely on the N side and that there is a very small depletion width on the P side. Part C, what is the current when there is a forward bias of 0.6 volts across the diode. So, now you have the diode to be forward bias, the external potential V is 0.6 volts. So, when you apply an external potential, the barrier height is lowered, so that there is an increase in current due to the minority carriers diffusing across the junction. In this particular case, the current density is given by a constant Js naught times exponential EV over kT minus 1. Usually the exponential term is much higher than 1, so that this can be written as Js naught exponential EV over kT. Js naught is your reverse saturation current, and this is given by Ni square E dH over LH Nd plus dE over Le Na. So, we saw the derivation for this during the course notes, but this is your reverse saturation current and this is something that plugs in here. So, if you remember the assignment from the Schottky junctions or the metal semiconductor junctions, we had a similar expression to this, except that the constant out front had a different value which depended upon the thermionic emission, but now here we have a PN junction. So, the constant here is your reverse saturation current. In this particular problem, Na is much higher than Nd, and since they are in the denominator, this term will essentially dominate over the other term. So, if you this is the reverse saturation current density. To calculate the current, we just need to multiply this by the area. So, all the numbers are here. We calculated dH and LH in part A, Na and Nd are known, Ni is also known. So that J S naught, so instead of J S naught I will directly write I S naught, which is J S naught times the area. So this is 8.36 times 10 to the minus 14 amperes. So the reverse saturation current is essentially a really small value. Once you know I S naught or J S naught, you can calculate the current during forward bias. So I nothing but J times A, which is J S naught times A times exponential E V over k T. V is 0.6 that is given. So the current works out to be 0.96 times 10 to the minus 3 amperes, or 0.96 milliamperes. So the current in the forward bias is 0.96 milliamperes. So that is nearly 10 to the 11 orders of magnitude, or 10 to the 10 orders of magnitude higher than the reverse saturation current. This is why we essentially call a PN junction to be a rectifier, because it conducts very well during forward bias and the reverse bias current is very small. So let us now go to part D. Part D, we want to estimate the forward current at 100 degrees. So the temperature is now increased. You can write this in Kelvin, so that is 373 Kelvin. The voltage is the same, so V is 0.6 volts. The question also says that assume the temperature dependence of Ni dominates over everything else. So over the diffusion lengths, the diffusion coefficients itself, also the mobilities. So if you only take Ni into consideration, so we can see that the current, or if you write this down, J is J S naught exponential E V over k T. So ratio of J at 373 Kelvin to that at 273 or 293 Kelvin. So this should be 373. So 373 by 293 Kelvin or 297 Kelvin, which is room temperature. So let me just draw this, write this as 297, is nothing but J S naught prime or J S naught at 373 Kelvin divided by J S naught 297 Kelvin. So the potential is the same. So the ratio of the currents or the ratio of the current densities is nothing but the ratio of the reverse saturation currents. This is directly proportional to Ni square, so that this is Ni square at 373 Kelvin divided by Ni square 297 Kelvin. Ni square is nothing, or Ni square root of Nc Nv exponential minus Eg over 2 kT. So for this problem we can take Nc and Nv to be independent of temperature. So the ratio of Ni's is just given by the exponential term. So if you do this, this ratio works out to be approximately 100, so that the reverse saturation current is increased by 100 when we go from room temperature to 100 degrees C. So the new values of Is naught 100 square. So the new values of Is naught at 373 Kelvin, just me write down the final answer, is 8.36 times 10 to the minus 10 and current I at 373 Kelvin is 0.10 amps. So that the current essentially increases by 4 orders of magnitude. In part E, we want to calculate the reverse current when you have a voltage of 5 volts. So, we want to know the reverse current when VR is 5 volts. To calculate the reverse current, we first need to calculate the new width when you apply a reverse bias. So, the width W is 2 epsilon naught epsilon r V naught plus VR, and we said that the depletion region lies almost entirely on the n side. So, I only have E and D whole to the half. So, this formula is something we used before to calculate the width of the depletion region when you have a p-n junction under equilibrium. So, we only modified it to add the reverse bias voltage, and we also removed the contribution due to Na because Nd is much smaller than Na. So, we can plug in the numbers. The new depletion width comes out to be 0.88 micrometers, and most of this is in the n side. So, when you have a reverse bias, you have thermal generation of carriers within this depletion region, and this thermal generation of carriers is responsible for your reverse current. So, I gen, which is the current due to thermal generation of carriers, is E times the cross sectional area times the depletion width times Ni divided by tau g, where tau g is the thermal lifetime of the carriers, and that value is also given. So, everything here is known, we can substitute the numbers, and I gen works out to be 1.41 times 10 to the minus 9 amperes. So, this number is again much smaller than your forward bias current, which is of the order of milliamps. So, once again, even if you take thermal generation of carriers into account, we essentially have a rectifying action in a p-n junction. So, let us now look at the last question. So, problem 5, you have a germanium p-n junction diode. So, it is germanium p plus n, the values are given. So, Na is 10 to the 18 per centimeter cube, Nd is 10 to the 16, dH. So, dH I will write on this side. So, dH is 49 centimeter square per second, dE, because we are looking at minority carriers, is 100 centimeter square per second, tau E is equal to tau H, which is equal to 5 microseconds, and the cross sectional area is 10 to the minus 4 per centimeter square. So, we want to calculate the diode current. So, we want to calculate I when we have a forward bias V of 0.2 volts, Ni is 2.4 times 10 to the 13 per centimeter cube. So, this is very similar to the previous question. So, J is Js naught exponential EV over kT, and then Js naught is Ni square over E dH over LH ND plus dE over LE NA. So, all the numbers are given. So, Js naught I will just substitute and write the final answer, but you can directly do the substitution. Js naught is 2.94 times 10 to the minus 5 ampere per centimeter square. So, the current Is naught is 2.94 times 10 to the minus 9 amperes. Once you know Is naught, you can substitute here and you can get the current. The current I is nothing but 6.687 times 10 to the minus 6. So, in this particular case, the difference between the current and Is naught is not as high as in the case of silicon. One particular reason is because your applied voltage is very small, it is only 0.2 volts. Another difference is that the material is germanium, so that the band gap is smaller, so the built in potential is also smaller. At the same time, Ni is larger, so that Js naught is also larger. So, these are some of the factors you have to take into account when choosing materials for forming p-n junctions.